Hello there and welcome to another video from Lockdown Electronics with me, Bill, and today we're going to be looking at how components change their value in response to change in temperature. In particular today I'm going to be looking at capacitors. Now you may recall, if you've been looking at any of my videos, about this machine, which is the Hantek 2D72. It's an oscilloscope, multimeter and signal generator, and when I reviewed the software, I'll put a link somewhere up there for you to click on if you want to see that review. I discovered the software has the ability to save some of the multimeter measurements as a CSV file. So I've been using that feature with the machine attached to my computer to see what happens to components when they undergo changes in temperature. So that's what today's about, so let's go and do some experimentation. Okay, first of all, a word or two about the methodology. When I was studying for my amateur radio exams back in the 1980s, I can remember seeing little snippets of circuit diagrams where in the oscillator section of, particularly of transmitters but also of receivers, there was a particular type of capacitor which had a negative temperature coefficient, and that was to try and generate some level of stabilization for the oscillator. In these modern days of fully synthesized radios, all those issues have pretty much gone. But I've got this receiver here, which is a Codar CR-70A, which I restored. It's a 5-valve HF receiver, and I actually quite like using it. I've also got the pre-selector as well, which again is a single valve unit, which dramatically improves the performance of the radio actually. But one thing it definitely does do, it drifts. When you switch it on, tune to a frequency, and sure enough, within 30 minutes or so it won't be on that frequency anymore. It takes it about between 30 and 60 minutes to fully stabilize. So if you think about a single sideband signal, which is roughly about, between 3.5–5 kilohertz wide, obviously the radio can drift away from that quite quickly. So I was interested in finding out what happened. So what I did, I installed inside the top of the radio here, and I'll show you some video in a moment or two of how I did it. I installed a couple of capacitors and also the thermocouple from my multimeter so I could measure the temperature, and we'll see what happened coming up. But it then sparked my interest into quite what was going on particularly with two different types of capacitor. And here I've got an old polyester one and also an old ceramic one from my junk box, and I got quite an interesting response from this particular ceramic. Unfortunately it hasn't got any markings on it, so it's hard to know what it was originally, but it sparked my interest sufficiently that I got a conventional ceramic, and it's actually inside that heat shrink there along with the thermocouple probe, and I wanted to measure them too to see what happened when they were warmed up. So we'll also look at that data, but first of all let's look at the radio. So here we are listening to Shannon Volmet on 5.505 megahertz, sorry, and they just switched the receiver on, so it's still very much warming up. That feels cold to the touch.
120 degrees, 5 knots. Wind varying between 080 degrees and 140 degrees. Tide okay. Temperature.
So the voice there sounds about right, and as you listen, as I'm
1025 low sig. Repeating, Frankfurt, Metroport, Frankfurt at 09020 Zulu.
So as you can hear, it's drifting as you would expect as it warms up, and obviously the Shannon Volmet signal is single sideband, so it's very stable, and that transmitter clearly is fully warmed up as it's on 24/7. So if you listen now, so you start to get that slight change of tone as you do get with the sideband signal as it's not quite in tune. So if I now retune,
12 knots. Wind varying between 130
maybe slightly low there, but not actually that far off. And
temperature 10.
sounding quite normal now, as you can see, it's drifting.
1025 06. Repeating, Luxembourg, Metroport.
And that drifting, of course, is a result of components beginning to warm up inside the case. So I thought it might be worth looking at how much the change actually is. So let's now set up the little experiment and see how we get on. Okay, so here's the Codar valve receiver, and as you can see, it's metal enclosure. It's just thin sheet steel, and when it's in use that gets quite warm. There's also the pre-selector, which also has a valve in that sits on top here, so I shall be doing the test with that on there, but it would be in service. There is a gap at the back here, about maybe 1.5 centimetres, which does allow some ventilation. But if I now take the top off and just move that around a little bit so you can see it. So what you've got here is obviously a transformer that's the mains transformer that makes a little bit of heat, and then you've got 5 valves that obviously have heaters in them and produce a great deal of heat. And there's also a couple of bulbs, I suppose we shouldn't forget those too, because they'll generate some heat. And the ventilation gap is at the back here, about there. So the heat rises and will eventually, I guess, drift out the back to a certain extent, but pretty much in here it's going to be quite warm. So what you've got the 2 IF transformers in here in aluminium cans. You've got the part of the RF input coil here, and then you've got the 2 gangs of the tuning capacitor. So you've got one for the RF input and one for the oscillator. That's aluminium, obviously air spaced, and it's quite within quite close proximity to the valves. So yeah, it's going to get quite warm. So my plan is quite simply to see if we can measure just exactly how warm that is. So I've got this set up here, which hopefully you can see in front of the camera there, and I've got 2 capacitors. I've got this polyester one, and I've also got a ceramic capacitor here, which experimentation suggests that's got a positive temperature coefficient and that's got a negative temperature coefficient. And there, tucked away as well, is the thermocouple from one of my meters, and that's going to allow me to measure the temperature in the area of those capacitors. So I've insulated them well, as you can see, and the plan is to place them somewhere in this region, not quite sure exactly where yet. Take some measurements when it's cold, maybe even do it that way so I can get out the back of the set quite easily. Take some measurements when it's cold, let it warm up, and then see what difference that actually makes. So I'm going to find a way to fix that, and then I'll show you how I'm going to do it, and then we'll make a start on some testing. Okay, so here's the arrangement I've managed to get inside the radio. So here's the 2 capacitors that I want to check. There's the thermocouple, and I've just cable tied them to this IF transformer here, and tugging the cable doesn't really make very much difference, and it's actually means the test components are actually positioned right next to the 2 tuning gangs for the oscillator and the RF front end, and that's exactly where I want them really. They're also reasonably near to that coil as well, and obviously you've got a valve in fairly close proximity. So I'm going to put the lid back on, I'm going to get it back into its installation position, and then take some initial measurements. But I'm pleased with that. There's no way that's going to, that doesn't move at all. If I have to pull that quite hard for even to get a slight movement, and it certainly isn't going to come into contact with anything inside the radio. So we'll get measuring now. Okay, so here's the general setup. I've got the radio back in its case. I've got it positioned against the back wall here, which is where it would normally be, and the pre-selector here, which is effectively an RF preamp, has also got a valve in, and it would normally sit there, and obviously it's got an impact on how easily the heat can get away. So I'm trying to recreate normal working conditions as closely as possible. So I've got thermocouple here, and for about the last 20 minutes it's been steady on 21 degrees with the radio switched off. I've measured the two capacitors using my East Tester E3240 bench meter. I've taken 50 measurements of each capacitor. I've got the average and I've got the standard deviation recorded, and also the time. So I'm going to switch on now at 10:47, and I'm going to let it warm up, and then we'll try and find the frequency once we get some audio. Here she comes. Okay, that's Shannon Volmet tuned in, so I'm going to let it settle down. Normally it's reasonably stable after 30 minutes, and it's pretty good, about as good as it gets after about an hour. So I'm going to check every 10 minutes or so and see what goes on. So we'll see how we get on with that. Okay, well that's about 2.5 hours since I switched on, and as you can probably see from the meter, the internal temperature is now at 40 degrees, and it's been there for at least 35-40 minutes, so I think that's probably considered stable. It's pretty much stopped drifting as well. Yeah, I would say the drift there is absolutely minimal now. So I'm going to switch off, let it cool down, and then see how the capacitors return to normal, and then we'll look at graphing up the data and see what we can see. So here are the test results then. So first of all, a graph that shows the temperature change inside the CR-70A, and as you can see, temperature rose fairly steadily up to about 35 degrees and then began to level off for the last 5 or so degrees. I had two capacitors in there. First of all, I had a ceramic capacitor and also a polyester capacitor. And the ceramic capacitor again rose steeply in line with the temperature, but probably at about 35-36 degrees it began to plateau off and it began to fall, and eventually ended up at 45 degrees, slightly lower than its peak. Whereas the polyester capacitor, as you can see, rose up fairly steadily. The two plateaus have got more to do with the resolution of my measuring instrument, and I suspect that would have been a much smoother curve had the machine been capable of a better resolution when I was measuring that capacitance. What's all that mean? Well, the implications for frequency stability then, if we take the ceramic capacitor and we assume that's going to be in a conventional tank circuit, so that's a coil and a capacitor in parallel. The frequency of a circuit like that is governed by the formula reciprocal of 2 pi times the square root of L times C, where L is the inductance in henries, C is the capacitance in farads. So if we assume a 1 Henry inductance and a 1.2 nanofarad capacitor, this is just an example, it isn't what's inside the radio, but just to give you an idea. At 10 nanofarads we get a resonant frequency of 1591 kilohertz. At 12 nanofarads, which is the change that we saw inside the radio, we get a change to 1452 kilohertz, which is equal to about 139 kilohertz change in resonant frequency. And just bear in mind that that's most SSB signals are between 3 and 5 kilohertz wide. So you're looking at probably over 30 channels worth of frequency drift there. So it's the frequency drift is understandable. Okay, let's look at the specific example now of the radio. So for the Codar CR-70A, here's a schematic of the front end, and here's a photograph of the top of the chassis. And first of all, you can see there are two tank circuits that are tunable in there. This one here, which is the front end with an airspace coil, and the tuning capacitor next to it, labelled 50, is actually the trimmer capacitor for tuning the aerial tuning. And the other tank circuit is this one, the other half of the gang, which is the oscillator. And the gang capacitor is there, and it's those two on the actual circuit diagram. It relates to that large aluminium variable capacitor that's in the centre of the radio. The airspace coil is also on the top of the chassis there, and you can see it's got a number of taps depending on the waveband that you're using. And the coil that's associated with the other half of the tank circuit for the oscillator there actually is one of those little blue hexagons with a hole in the middle that you can see, and that actually corresponds to there's four of them, because there's four bands. There's just one shown on the circuit diagram for clarity, but that's actually underneath the chassis, and you can see them there. They consist of 4 little transformers, and each has a trimmer capacitor in parallel with it. When you come to adjust the oscillator for each band, the coil slug adjustment allows you to adjust the bottom end of the band, and the trimmer capacitor normally allows you to adjust the top end of the band so that you can get it in synchro with the tuning dial. But the obvious implication there is there's going to be quite a difference in temperature underneath the chassis compared to being on top, where there's a fairly large transformer and 5 valves. So maybe a project for me at a later date is to actually get the thermocouple inside the bottom of the chassis and see what the temperature difference is. But we've obviously got differential heating between one half of that tuning gang capacitor and those coils that are underneath. So again, that will have some impact on the frequency drift. Okay, well that's the results for the Codar CR-70. You can see behind me. What prompted me to start all this was some unusual measurements I got off a ceramic capacitor, and so I just want to show you those results because they were quite surprising, and they're certainly going to be the subject of a future video at some point when I've begun to understand the results that I've been getting. So just have a look at these. Okay, so I mentioned earlier on that one of the things that intrigued me here was that I'd got quite an unusual response from a component, and the component in question is that small ceramic capacitor there. You can see it there, it's attached to the polyester capacitor and also to the thermocouple to allow me to measure temperature. So I rejigged this arrangement and I measured that capacitor, heating it up to 70 degrees and then letting it cool down, and wasn't really sure what was going to happen, but this is the curve that I got. So there we are, starting off at about 21 degrees, there we are up at 70 degrees. I used a heat gun to heat it up to that temperature just gently, and eventually it returned back to 21 degrees, and that is the curve that I got. Now I've actually done this measurement twice and got similar results on both occasions, so I'm intrigued, and this is definitely going to be something for a future video. I need to explore this a little bit more and maybe look at a couple of other ceramic capacitors and see what kind of response I get. Okay, I hope you've found this video interesting and useful, looking at what happens to capacitors when they get warm. I've certainly got more work to do based on the interesting results that I've just shown you, so that's going to be something for the future. Keep me entertained. Thanks very much for watching. If you've liked it, please click the thumbs up. If not, you can click the thumbs down. Either way, still appreciate your interest. Be great if you could subscribe, and look forward to seeing you on the next video.